This research project sort of summarizes quite an interdisciplinary journey that I had until that point, which I'll take a couple of moments to share with you. So I started out as a computer science undergraduate at the Technion in Israel. Then I worked as a software engineer at Intel for a couple of years. After that, I switched to the most abstract thing possible. I did a master's in logic and in formal semantics, continued to do a PhD in computational linguistics and NLP. And then I had two postdoc positions, one in linguistics at Uppsala University and another in the research group of Professor David Harel software engineering research team. So in 2014, I joined the faculty of the Open University in Israel and opened the research lab there that sort of unifies these different threads of work. In 2015, 2017, I did create two non-artificial agents. We're quite good learners, better than Bert. And since 2018, I'm back in full force leading the ONLP lab. This is the name we gave it, the Open University Research Lab for NLP and Artificial Intelligence. I have a diverse group of 8 researchers. They come from diverse disciplines: linguistics, computer science, data science, software engineering. And we have 3 core projects. The first one is we're actively developing infrastructure for Hebrew NLP. We're actually the only team that's doing that. We've released various accurate tools, and this is quite challenging. As Noah said, it gets us into a lot of research into multilinguality and linguistic diversity and typology. It's fascinating, but it's not what I'm going to talk about today. The second project, which I named Deep Models for Deeper Semantics, is where we try to explore neural network models for predicting and investigating nuanced semantic notions. I will say a little bit about that towards the end of the talk. And the project I'm going to talk about today is natural language programming. This has been going on for a couple of years now. We're sort of in the second cycle. And here we try to answer a very interesting, long-lasting question in artificial intelligence, whether or not we could program computers in our own native language. So this is not a new question. This question was around almost since the computers themselves came into existence. And Dijkstra, whom I'm sure you all know, wrote a very famous note called On the Foolishness of Natural Language Programming, where he argued that this will be very difficult to make and to use. More specifically, he talked about the ambiguities in natural language, and he said that in all of our communication with computers, we must stick to formal languages. So that was 4 decades ago. And now, 4 decades later, we communicate with computers and artificial agents in our own natural language in various domains, right? We ask them to search for queries, translate. We have digital assistants that can execute commands like, remind me to call mom on Monday, or what is the weather in Seattle now? And that's already quite impressive if you compare it to Dijkstra's prophecy. But this is not quite what he meant, right? So when he was talking about natural language programming, what he was talking about is giving an actual system description. I'm going to use this as a running example throughout the talk. The user flips up one card and then flips up the other card. Afterwards, the system checks the cards. If they match, they are discarded. If not, the user can start over. So this is like a memory game sort of simple application. And what we want to get back is the executable that can actually run this system. So the goals of the projects are precisely this. We would like to interpret these sort of descriptions. We would like to be able to execute them. And we would also like to hopefully be able to learn from the outcome of the execution. These are the sort of goals, the high-level goals of the NLPRO project. Now, I would like to very briefly survey this topic from the 2 main disciplines that are involved in this topic. So if you think about software engineering, or the history of software engineering, we've been moving from very low-level languages, right, bits, zeros, and ones, to sort of higher-level languages. And today, in software engineering, people develop controlled languages. These are languages that look like English. They're very readable, but they're not ambiguous. They're strictly formal languages, and use them to specify and implement complex systems. And the question is whether we can make this leap from controlled languages to actual natural language? This is a big open question. People in software engineering have been trying to do things in this domain, but they mostly remain with more and more expressive, controlled languages, not letting any ambiguity in. Now, in natural language processing, we already know how to handle ambiguities. So we've initially learned how to process sounds, and then words, and then sentences. And already today, we have people working on translating sentences to some executable forms, such as an SQL query or a regular expression of some sort. These usually go on sentence level. And this is not exactly what we're aiming for. What we really aim for is to assign a complete meaning to a document and get the complete executable in return. And the general claim that I make is that I think the time is ripe for that. I think that advances in natural language processing, when we can effectively process very difficult ambiguities, and as well as advances in software engineering that allow us to synthesize complex systems, would allow us to actually achieve, or at least try to tap into this very interesting domain. So how are we going to do that? So first, I would like to introduce the 3 key ideas that sort of lead this project. And then I'm going to tell you a little bit more about the details of what we've done in the first cycle and what we started to do in the second cycle. And hopefully, I'll have time for a very short demo. So again, we have this memory card example. And the first key ingredient that I think is really very important is how we represent the semantic meaning. So far in NLP, we usually go, system semantic power, so usually go for what I call static semantics. Static semantics is something that's sort of focused on the predicate argument structure, can extract entities, can extract relations. So the user clicks card A, we have an actor user, an action click, and then a card that's being acted upon. But there are multiple other elements, like and then clicks card B, or must then check the cards. And if they match, they are discarded. We actually don't have explicit mention of all of these, but we do have a very clear workflow and relation to what happened before. So these are quite complex relations. And my first claim is that if we actually want to have the expressivity to be able to compile code out of language, we need a better representation. And I suggest that we actually think about the semantics of a process as a running code. And I represent it how software engineers represent this, using what they call a life sequence chart. So in a life sequence chart, we have the entities, so the user, the system, the cards, timelines, so the lifelines going top to bottom. And then we have events and control structure to sort of constrain the execution. And once we move from a static sort of semantics to a dynamic process representing the semantic, I think we're at a better starting point to get the expressivity that we want to then be able to execute. So now we want to assign this kind of semantics to sentences or documents. And the way people currently do this, mostly in software engineering, actually. So they get the best state-of-the-art tool that they have from NLP. It can be, some people use spaces, some people use embeddings and do stuff with them. You could use BERT, can use any sort of thing that goes out. And on top of it, try to sort of construct something that will put the seed of the executable. This is a tedious process. It's specific for every domain. Definitely doesn't generalize, and actually doesn't even cover everything, because the tools don't have the expressivity that they actually need if they do requirements engineering, for instance. So what I propose is that the modeling that we do takes both text and code into account at the same time. So while we interpret the text, construct the code. While we construct the code, we get this to disambiguate what we don't yet know in the text and get this feedback loop going, so we can get more and more constrained, more and more accurate representation, which is hopefully what the writer had in mind. So this joint modeling thing, we tried this for a couple of domains: morphology and syntax, syntax and semantics, semantics and discourse, and we believe, and also actually later show, that this is very useful also here. Okay. Lastly, I propose that it be a learning architecture. This is not new for anyone here, but this is rather new for people coming from software engineering. We want to learn from naturally occurring examples of text aligned to code. And since we have the executable, there's also the idea that if it doesn't execute, it doesn't compile, or the simulation goes well, there's also a signal that we can use maybe to improve learning. So these are the three key ingredients we'd like to sort of further develop in order to be able to achieve this natural language programming act. OK, in order to do this, to actually construct the architecture I just showed, we have to answer 4 questions. We do this in cycles. So we first ask what's the representation, what's the granularity of the alignment between the text and the code. This is not a trivial question. We want to model this so that we can learn a statistical model and generalize. We want a parser that will be efficient, so we'll have to construct the system, and there are going to be multiple systems that are possible. And we want to validate that it actually does what we want it to do. It could be intrinsic evaluation, or it could be extrinsic. So it could be inside some sort of a task that uses language. In the first cycle, we were focusing on quite short requirement documents and turned into executable live scenarios, like the ones you just saw. I will show a case study with statistical modeling and show the difference between what happens in sentence level and discourse level parsing. And I'll show it with certain intrinsic measures that we develop. But then towards the end of the talk, I'll show you various alternatives with like other tasks and other models. OK, so let's dive into the actual details of our first proof of concept model of this. We assume that we have a document, that the document represents the system, and this consists of n, what I call scenarios. A scenario is one sentence that represents one aspect of the behavior of the system. It doesn't mean that system requirements go like that, but it is what we assume for starting with. And in our case is so not very big. It's like dozens. And scenario is something like that. When the user clicks the button, the display color must change to red. And to interpret that, we have various things we have to understand or interpret. We have to know what entities are there, what attributes, what values are there, events. We need to know the modalities, if something must or may happen. We need to know the quantification status. We need to know if this is a button or the button. Is it a new one or an old one that we're already familiar with? We need to know the timeline. So what happens after what? We need to know the conditions. And here, everything is important. So this comma is like when something, then something. So everything has to get interpreted. We cannot skip any bit of information from this paragraph if we want the text-to-code thing to work. So what we're going to need is a way to represent all these bits of information. And this is where we choose to work with the live sequence charts. This is a formal visual programming language that was developed by Professor David Harel from the Weizmann Institute and colleagues. It's an extension of the unified modeling language that software engineers often work with. The two important things about live sequence charts is that they can be synthesized at runtime. So if you have a system and you add another chart, it can be synthesized into the general process, and that they have direct and unambiguous translation into code. So once you have your LC, it's executable. So that's a very important property for us to, and this is what we build on, like on progresses with software engineering. This is how it looks like. So we have the timeline. It goes from top to bottom. We have the entities represented by other lifelines. We have messages that are events, actions between entities. We have properties that can be marked, can be accessed through these arrows, reflexive or non-reflexive arrows. We can change the values through these events. And we have modalities. Modalities is whether something can or cannot happen, may or may not happen. So a red thing must happen, but the blue thing, it can happen, but you can wait, and it might not happen. So that's something that's important for program flows. And we also have conditions. In fact, we have all the control structure you may be interested in. So it has loops and switches and complex conditions. So everything you might want in order to implement a control flow. So this is the output representation that we're interested in. aside, well, next to the input representation, we actually want to have the code, right? So we have n sentences, scenarios, and we have each scenario assigned with an LSC. So we want to have the code that is needed for executing the scenarios that is described by the LSCs. So our task is to get this requirement document, parse it into a sequence of LSC charts, life sequence charts, and at the same time create the system model that's the actual code, in our case it's Java code, the actual code that's needed in order to execute the life sequence charts. In our terms, we said that this is the code that grounds the execution of the life sequence charts. So that's the task. OK. How do we model it? So here we start with something that is very common to do in NLP. So we start with the noisy channel model. We have a slightly different metaphor than the ones you know. So we assume that there's a system analyst, that in their head, they know how the system works, right? So they know what they want. It doesn't have bugs. It has all the functionality and the non-functional requirements, but they cannot code, right? So all they can do is to deliver some noisy description in text of that system that is really perfect in their head. So in our model, we need to recover what they have thought about, or created through this noisy channel, through this document. So this is a standard thing to do. We do the standard manipulation where we get rid of the constant in the denominator, and we have two models that we have to estimate. So we have one, the channel. Given the system model, the code, what's the probability of the document that we have in our hand, and the prior probability over this system model. So this is nice, but this is also quite complex. We cannot really work directly with it. We need to break it down further. So first, what we're going to do with the source. So this is the code that is going to be used for running the entire system. And what we do at this point is we break it down to a unification of what I call system model snapshots. The system model snapshots are, in fact, parts of the code that are relevant for executing each one of the requirements. And we model it as system model generates the description for the particular requirement, position I. By the way, there can be more than one life sequence chart here, so we may have to marginalize over several life sequence charts that connect the code with generating the requirements that describes the behavior of the system. We also have a very, very light signal, but it is there. The signal concerning the sequence in which these requirements were transferred to us. It's nothing big, but it's there. And this gives us what you can view as a simple hidden Markov model in the sort of classical statistical modeling terms, where you have transition probabilities from one system model snapshot to the next in the sort of phases of development, and the emission probabilities, which we take to be the probability that a given snapshot of this code generated a certain behavior, so a sentence describing the behavior. So, OK, so I'm going to first quickly tell you how we're going to estimate this parameter. And then I'm going to tell you how we're going to construct the system efficiently and get the one that's most probable based on what requirements we were given. So the emission probability thing is quite standard. So what we do is we marginalize over the trees that express the description and the system model snapshot that's relevant to this position, or we marginalize over all trees that are relevant to a certain system model snapshot. Once we can transfer this expression to be marginalization over trees, this is quite easy. So we use a simple PCFG to estimate that. And the way we do that, we use a tree bank from requirements developed at the Weizmann Institute at the software engineering team. So these are several case studies that were developed regardless of what we did, actually much before I came there. System requirements that work of simple things like a clock or a baby monitor or a vending machine, right? Simple reactive systems. There are syntactic trees This was developed by a PhD student, Michal Gordon, at the Weizmann Institute. It's similar yet different from what you would see, for instance, in the Wall Street Journal pen tree bank, but you know, the technique is the same. So I'm not going to go into the linguistic description of these elements in the tree bank, but the most important property for this grammar is that for each node, we have a composition operation, how to create the internal node, so the entity or the event or the control structure from the daughters. And this compositional semantic operation is what allows us to build from this tree both the live sequence chart, the LSC, describing the behavior, and the bit of code, the system model snapshot, that grounds the execution of the semantics of this tree, right? So we have the syntax, the semantics, and grounding it in actual code. So if we have a tree bank and we train it, we can have a probabilistic grammar and get the most probable emission. Well, we can get emission probability and get the most probable tree. And if this works perfect, then we're done. But we have something which is, if you want to completely model the complete document, the complete system, we also have transitions. Transitions are this moving between one state of a system model snapshot to another. And this is something we don't have a grammar for. We definitely don't have a tree bank for. And we need to, anyway, try to estimate these parameters. And what we do here, we actually rely on this really, really weak signal of order, and we call Bryce to the rescue. So Bryce is a philosopher. He worked on cooperative communication between humans. And he had the so-called Bryce Maxims. I don't know if you've read this. And these Bryce Maxims say stuff about how people convey messages. So what they say, for instance, is that people are economic. So they only convey what's needed and not more than that. Bryce also said that people are informative. They'll give as much information as you need. That people are truthful. So they give you all the correctness of what they believe to be correct. And relevant to what you want to know. So this is for cooperative communication. If you want to model something like people deceive someone, this wouldn't work. But if you're cooperative, this is supposed to be like the basic communication, not skills, but something more innate than that. So people do, well, that's the claim. People do communicate like that. And what we do is we get some measure to approximate these maxims. So max overlap, for instance, asked how much overlap there is between the two system model snapshots. So one of the maxims says that we need to have some sort of common ground between the speaker and the hearer, and the overlap says that there is certain shared knowledge between the speaker and the hearer. So I don't talk sort of over your head. I talk about something that we've already established. And the max expansion says the opposite. It says that I deliver new information, or maybe a lot of new information, because this utterance has to be informative. And the eddy distance looks at something else on how easy the transition is from one state, one system model state, to another. Because there's also the assumptions that people will not do huge leap, but more constructed steps. We turn it into a probability measure by normalizing on all the candidates, model candidates that we have on the system, and we got the probability measure to be able to train these transitions. Okay. So we have estimated the transition probabilities. We can estimate emission probabilities, but we need to infer what the system looks like, and that's going to be almost the hardest part, because there are very many system models possible. Even if you work with skilled software engineers, if you work with 3 of them, you'll get 3 different systems, probably. So let's take a look at a very simple system where we just, for each sentence, get the probabilistic model that we have for the trees, for each tree, each possible tree in the forest in this CKY chart, we get the live sequence chart that is created based on it, and the system model snapshot that grounds the semantics of the LSC. And we have n of them. So a simple model will just go requirements by requirement, and we'll take the best, sort of most probable tree, unify the system models that we get, and end up with a system. That's something we can do. We actually try to do, but we want to do beyond that. So we want to have the whole grid of possible system model snapshots and possible emissions. What we have on this y-axis is, so for each of these charts, we have a set, a finite set that we bound in the, so basically we bound it in 32 or 64 beams, so we don't use everything in the forest, but we use the k-based trees to generate for each one of these a candidate for a system model snapshot, and we sort of stack them all the way up. So we have n times n candidates times little n for the different requirements. We have a finite grid, and we go through the grid. The one path that will maximize the probability of emissions and transitions, so probable trees and probable transitions, is the one we choose, and then we unify all the trees, we unify the codes, and we get the system that will be running. So note that if we're not going down this path, so if we made the decision to go up, we have a less probable tree, but we are doing it for a good reason, because we think the transition is more probable for this piece of code, right? So it's not, we can also go wrong, but we believe that this will make us go in the right way.
Sorry, just to be clear, so the data are documents?
So I will now say precisely that. Okay. So what do we do and how do we do that? Getting the data is actually almost the hardest part here. So there are not so many system requirements that are aligned with the code. We are lucky to have these 5 case studies that software engineers developed for their own purposes. And we do a cross-fold experiment, which means that we train on 4 scenarios and we check on the 5th one. So basically, we're out of domain in each of these runs. This is not big. So all the scenarios, everything together is about 100 scenarios. So we also synthetically generalize live sequence charts from the probabilistic grammar that we have. We inject some noise, and once we have a syntactic tree, this doesn't necessarily compile into the semantics. So remember, we have semantic operations on the nodes. If the syntactic tree doesn't compile well, then we just throw away the tree. So we only use trees that have actually valid executable semantics. That leaves us with about 70% of the trees that we generated. And adding them to the training actually really, really helps. OK. So we also defined the experimental settings to have, so it's a very simple experimental setting. We have sentence-based inference, which has no context, just the most probable tree at every time point. And we have the discourse-based that takes into account the entire grid. And we have 3 measures. So the part of speech tags is just the role of the word in the requirement. It gets assigned the right role. The LSCF1, these are simply trees. So LS1s in the back of so the representation itself is an actual tree. We can simply run F1 measures on them. And we also do a TED three-edit distance measure, normalized three-edit distance, to get how correct we are with the actual system model. So the actual code that we generated relative to the code that we were given by the Weizmann Institute researchers. And this is the pattern that we get. So this is one example running on a simple phone scenario. That what you see on the right side is the sentence-based. So we have only one candidate for every tree. And what you see here is when you give several candidates for each sentence, you have multiple system model snapshots at each time step, and you choose based on the grid. And in all the experiments that we've done for the scenarios and for the different measures, we always found out that the context-based sort of inference over the entire grid is significantly better than the sentence-based model. And I should say that some scenarios are much easier than the other ones. So this has to do with sort of internal complexities of the case studies that have been developed. I wouldn't want to infer from it on how easy or difficult it is to translate text to code, but I do want to say that here it's really clear that context matters. So context has a very valuable disambiguating signal in it that if we ignore it, we actually are more likely to be wrong on an interpretation on a particular timestamp. Okay, so this was sort of across the board clear. I think in every future endeavor of this we do that. So we take into account in the model various sorts of contextual information. Okay, so we've worked really hard to be able to hook this computer in so that I can also demonstrate to you that this thing actually works. So the system I'm going to show you is a system that's called Playgo. Playgo is a system for drawing live sequence charts. Okay, so you can drag and drop various elements in order to create something that looks like a sequence chart and that's running. And what we added is this very simple, so actually we added only one function to this big system developed by the Weizmann Institute. We create a project. I'm creating a new one so that you see that it's empty. Okay, so there are no classes, there are only special classes, the clock and the environment. And what I add to the demo is just a text file. So, very simple. Let's call it to description. Okay, and let's take this. Oh, no, not this. Hang on a second. Throw it in. And what we added is this import description function. This is what you saw, so the grid. We call it, and we get the live sequence chart. So this is already nice. We have a formal language representing the execution, but this is not where it ends. We can actually execute it. So we can call the so-called playout function of this tool. We can select the model. Okay. Then it sort of calls all the formal operations, and it creates this dummy system with the properties and the classes that exist. Once you click it, you get the execution running. So if you want it, it's fast, but you can see that it takes track of the execution. If you don't want to, look at it, and you can look at the log and see all the points in the charts that were visited while it was executed. And yeah, you can use sort of multiple sentences to create more and more complex systems. So that works. Okay, that works, but it's not the end of the road. It's actually just the beginning, because what we've done, so it does give us a way to work without having to specify every bit or disambiguate everything for the computer, but it is still quite constrained, right? So the language that this tree-bound grammar allows, and the training that we had, means that this generalizes only so far. So if it understands what you wrote, then you get the LSE. If it doesn't understand, you get nothing. It's already a good start, but we want to do more. And if you want to do more, we have to do things for getting more linguistic phenomena in, getting from statistical modeling to neural methods, and also validate it on tasks. So in the time that I have left, I'm going to quickly walk you through 3 other projects that sort of follow up on this, on the different problems that this has, or challenges that this has introduced, and how far we've got with these various problems. Okay, so concerning how this would be relevant for tasks, we have a case study of this in the area of natural language navigation. So natural language navigation is you get the instruction, or in fact you work with stories, right, with sequences of instructions that will get you from point A to point B. And we want to pin this on a map, on a symbolic representation of a world, which is an actual realistic map. And we call it the run task, realistic urban navigation. Now, there's no visual sensors here, right? So other people are doing that. We're really focusing on interpreting the content of this algorithm of how to get from one point to another using this map. And we collected the data set using Mechanical Turk. We collected it over 3 regions of Manhattan, so it's a very dense sort of map with many information layers. The collection was done with 2 disjoint sets of workers. So we had the specifiers that specified the stories, and then we had the validators that validated the stories. And we ended up with about 400 stories, 2,500 instructions. And we worked with various sequence-to-sequence models, and we realized that the standard sequence-to-sequence with attention wouldn't work so well on that. But if we do several things, like adding the world state at each of these points, not only getting the world state, but also getting the attention to work on both the input sentences and the world state, and adding entity abstraction. Entity abstraction meaning that we're only working on the, we identify entities and replace them with a very, very small set of variables. So if the attention works on these abstracted sentences that represent the navigation language and the world state that represents the entities that are still there, we get the grounding quite right. This is going to be submitted to ACL 2019. Yeah, I'll be happy to talk more about it. Well, we don't have much time, but if you want to ask me about it, or later during our meetings. I also want to point out that when we're actually working with the data of natural language programming, we found out that a lot of semantic phenomena are not actually being treated currently by standard semantic parsers. So one thing that we see a lot, actually, is this phenomenon that's called bridging. So if you have a scenario like when you touch the display, the color changes to red, you need to find out what's the antecedent. So actually, you need to find out two things. First, that this color is underspecified, even though we can interpret it, and the color is an entity that we know what to do with it. We don't yet know at this point that it belongs to the display. So this phenomenon of finding these implicit relations of with the antecedent that's related through some property to a different noun phrase is something that's very important in our domain. And we have a project working on just that. Currently, we're just in the initial stages of designing the data collections, but we're also thinking about what models would be appropriate for this task. Another notion that's super important in our domain is cause and effect relations. Cause and effect relations are not entailments. So this is quite nuanced. So there are many models that can do entailments, but they're not exactly identifying cause and effect relations, which is something which is cognitively we're very, we're tuned to identify very quickly as human. We approximate studying cause and effect using a reordering task that is designed currently for the pro para data, which you know, I'm sure. The processes there give us a lot of opportunity to study cause and effect when you have to reorder what happened before something else. A third project has to do with the modality. This is, again, something that's super important in not in programming world, because in program scenarios, some things may happen, some things may not happen. And there's a distinction between actuality, so the things that happen in the world, and the things that could have been the case in the world. So one simple task is to identify the model element. What's actual and what's model, what could have been the case. But we actually need more than that, and what we do is we work to identify both the source, the red thing, the source of the modality, what caused the modality, and the blue thing, it's the so-called prejacent, so the proposition that's actually being modeled, right? The actual the non-actual proposition. And we classify it to model types. There are many. So modality types can be based on knowledge or belief of some agent. It can be based on circumstances, like the graphic card, on the ability or capability of doing something. It can be based on rules. So even a simple word like can, like I can swim 3 miles is about ability, and you cannot cross the street when it's I don't know, red light, right? So this is deontic. So there are different types of modality. They all turn out to be relevant for many tasks. So for natural language programming, for entailments, many entailments will hold or not hold based on these factuality detection, of course. And to identify them, you need a mix of context and syntax and lexical semantics of the actual word. We're working closely with linguists and experimenting with neural network models I don't yet know what to tell you which model will be best. This is, we're still experimenting with it. This is surprisingly complicated, but fascinating. So when identifying the model is somewhat easy, inferring the rest of it, so the span is relevant, and the type of modality is a little bit more difficult. The last thing I want to talk about is probably the main point that we need to solve before natural language programming could go large scale. This is something we found out only recently, again, when working with data for NLPRO. And it took us a while to sort of put it in the right terms. But so far, and also in this presentation, we asserted that people talk informally about programs. This is also what Dijkstra told us. So people, when they talk, they have these informal notions, and we need to make them precise. But the actual difficulty is that people think informally about programs. What does it mean? It means that cognitively, people that are not trained to do programming have a completely different way of viewing or describing algorithm, of constructing them in their heads. So one example is an excessive use of goto. If you remember, goto was once allowed before structured programming came into existence. So they will say, so people who are not trained, or children, there are lots of experiments on children in sort of psychology and education technology, will say, you do that, and that you do that, and then you go there, and then you do that, and then you go there, even if you can say it using a control structure, a simple structure like a loop, not to mention recursion, right? So it will be this sort of spaghetti code. This is how people will talk about systems unless you train them otherwise. So if you want to enable NLPRO, something that enables the crowd to program, there is a gap. Another sort of very interesting gap has to do with the perspective on the story. So there are actually three points of view. We have the player, the one that plays with the application. We have the actor, it can be a monkey. And we have the system. And in sentence life, if you want to get the banana, then you walk 10 steps, then you check that the banana is there, then you can fetch it. There are at least 3 players. And there's a very unique sort of ambiguity of which perspective is taken. When I got this, it sort of blew my mind. This is sort of ambiguity that I have never thought I'll have to handle. But it is there in the data. So getting the specification, knowing what the semantics is we can do that. But if we want the puzzle to solve connect well, we need to solve these sort of ambiguities, and these are hard. And we have a few examples, well, not examples, but ideas, how to proceed. But the more interesting thing, I think, is a strategic question. And I'm going to sort of place them here and wrap up the talk. So we have to ask ourselves how to model the gap between these thought processes, so how people specify programs, and how to infer the patterns that are actually structured programs. So this is going to be maybe Bryce, but not Bryce for communicating with people, but sort of HCI Bryce, so Bryce of how people will communicate with machines, or something like that. And there is a strategic question. So if we get a description and we can execute it, for instance, we get the life sequence charts right. So if the outcome is right, okay. If it's not, one possibility is to give a signal for the system to improve the interpretation. But another possibility is to give what's called in psychology an intervention for the person that's programming to get a different expression, more compact expression, more structured, more less ambiguous, and sort of build the seeds for the most structured program in the thought of the person programming. This is called computational thinking. It's actually very, very high on everyone's priorities. All parents want their kids to have that computational thinking. So I imagine it could be a mutual learning process, so that we have a learner, artificial intelligence that sort of gets the execution in small bits, and then someone that can use the signal to sort of improve the pattern of thinking. So we're working on some sort of interface that's not very different from what people use to teach kids to program, but to do it in a natural language. Okay. So what I tried to convince you today was that it is extremely interesting to work on programs where you want to extract a formal executable system from some sort of description. We try to move from extracting entities in relation to actually interpreting every bit of the text and also implicit bits, right, the ones that are not there. We want to make the point that parsing sentences is a lot worse than parsing discourse. This may be more complex than we want, but in terms of disambiguation, it's a lot more informative. And when you parse for programs, there are a huge space of programs that are passable. This is something that's very useful to constrain the space of likely programs that the person had in mind. And we are now experimenting with various sorts of outputs in this program. So we have executable scenarios. We have now roots on maps, and CT, so computational thinking thought processes, if you will. That's it. Thank you very much for listening. I believe that this will get us to deeper natural language understanding and interesting interactive programming methods that not yet exist. Yeah, and I'm happy to take questions. Thank you.